Hello, everyone, and a warm welcome to the introductory module on organic chemistry. If you have some experience with cooking, you know how a variety of spices can enhance food flavor, often transforming a bland dish into a culinary delight. The characteristic flavor, aroma, and color of each spice come from various organic compounds. For instance, your morning cinnamon rolls get their flavor from cinnamaldehyde. Curcumin gives turmeric its bright yellow color, and cayenne pepper and other hot peppers derive their heat from capsaicin. Except for a few inorganic salts and water, nearly everything we consume or apply to our bodies consists of organic compounds. This includes food, medicine, cosmetics, and clothing, to name a few. Organic fuels are essential for warming our homes, cooking our meals, and powering our vehicles. As a result, major industries focus on producing organic compounds, including plastics, pharmaceuticals, and insecticides. All organic compounds contain carbon, which is typically bonded to one or more other carbon atoms, hydrogen, and often other elements. The same chemical principles you have learned so far apply to both inorganic and organic compounds, and their behavior can be understood by examining the properties of their elements. In this module, we will briefly survey various classes of organic compounds, examining their properties and reactions. We will start with hydrocarbons, which contain only carbon and hydrogen atoms. Our discussion will include hydrocarbons called alkanes, which contain only single bonds. I will introduce you to the principles of structural drawings of organic molecules, and we will have a short discussion on isomers, compounds with identical compositions but different molecular structures. Next, we will explore hydrocarbons with one or more double bonds between carbon atoms, called alkenes, and those with one or more triple bonds, called alkynes. In the lecture describing alkenes, you will see how our vision works at the molecular level. I will then introduce you to aromatic hydrocarbons, which have at least one planar ring with delocalized electrons. Finally, we will discuss functional groups found in organic molecules, which play a central role in the function and chemical behavior of many organic compounds. Although there is nothing mystical about organic molecules, their indispensable role in biology and industry leads many to wonder if carbon is somehow special. Of course, each element has specific properties, but the atomic properties of carbon provide it with bonding capabilities beyond those of any other element. This exceptional behavior leads to two key characteristics of organic molecules: structural complexity and chemical diversity. You may have noticed that organic molecules often have more complex structures than inorganic molecules. A quick review of carbon's atomic properties and bonding behavior explains why. You may recall from the introductory module of this course that carbon has 4 valence electrons. It is ideally positioned between metals and nonmetals in the periodic table, making the complete loss of electrons energetically unfavorable. As a result, carbon does not form purely ionic compounds. On the other hand, being centrally located in period 2, carbon has an electronegativity that is midway between that of the most metallic element, lithium, and the most reactive nonmetal, fluorine. Consequently, carbon forms covalent bonds of varying polarity with many elements across the periodic table. The number and strength of carbon's bonds lead to its ability to undergo catenation, which is the ability to bond to one or more other carbon atoms, resulting in a multitude of chemically and thermally stable linear, branched, and cyclic compounds. Although silicon and several other elements also exhibit catenation, none form chains as stable as carbon's. Carbon has 4 valence electrons and forms 4 bonds in virtually all its compounds. These 4 bonds point in 4 distinct directions. In addition, carbon's small size allows it to approach other atoms closely, resulting in relatively short and strong bonds. The carbon-carbon bond is short enough to allow the formation of multiple bonds, which restricts the rotation of attached groups, leading to additional structures and stereoisomers, which we will discuss in the lecture on alkenes. In addition to their complex structures, organic compounds are remarkable for their vast number and diverse chemical behavior. Several million organic compounds are known, and thousands more are discovered or synthesized each year. This diversity is based on the atomic behavior of carbon and arises from three interrelated factors, including the ability of carbon to bind with heteroatoms, differences in the reactivity of organic compounds, and the presence of functional groups. Many organic compounds contain heteroatoms, atoms other than carbon or hydrogen. The most common heteroatoms are nitrogen and oxygen, but sulfur, phosphorus, and the halogens are also frequently found in organic molecules. For instance, in this figure, you can see 23 possible molecular structures formed by various arrangements of 4 carbon atoms, a single oxygen atom, and a necessary number of hydrogen atoms to fulfill the octet rule. Please note that carbon and oxygen atoms can be either singly or doubly bonded. Finally, a central feature of most organic molecules is the presence of a functional group, which is a specific combination of bonded atoms that reacts in a characteristic way, regardless of the molecule it is part of. In nearly all cases, organic reactions occur at the functional group. Functional groups include carbon-carbon multiple bonds, as well as various combinations of carbon heteroatom bonds, each with its own pattern of reactivity, which we will discuss in a separate lecture. To sum it up, in this lecture, you have seen that carbon's small size, intermediate electronegativity for valence electrons, and ability to form multiple bonds contribute to the structural complexity of organic compounds. These factors lead to carbon's ability to catenate, which creates chains, branches, and rings of carbon atoms. The small size of carbon leads to strong, chemically resistant bonds that point in up to 4 different directions from each carbon atom. You have also seen that carbon's ability to bond with many other elements, especially oxygen and nitrogen, creates polar, reactive bonds, which is one of the key reasons for the chemical diversity of organic compounds. Most organic compounds contain functional groups, which are specific combinations of bonded atoms that react in characteristic ways. We will have a detailed discussion of this topic later. In the next lecture, you will be introduced to alkanes. We will explore the concept of isomerism, and you will learn how to draw and interpret organic structures. Thank you for your attention.